Hello, my dear students. Hope you all are well. Today we will discuss on wind energy. We have already discussed that the coal, petrol, etc. are diminishing. And today is the age of using unconventional sources of energy. Already we have studied how the solar energy can be used as an alternative source of energy today. Now we will discuss on wind energy. Wind energy. What is wind energy? Wind energy or wind power refers to the process of creating electricity using the wind or air flows that occur naturally in the Earth's atmosphere. Modern wind turbines are used to capture kinetic energy from the wind and generate electricity. Now, let us understand how we can classify different types of wind energy. We may classify it on the basis of production of energy. Firstly, we may say about utility scale wind. Wind turbine that produces in the range of from 100 kilowatts to several megawatts, where the electricity is delivered to the power grid and distributed to the other end user by electric utilities or power system operators. They may be classified in the class utility scale wind. Next, let us talk about distributed or small wind, where single small wind turbines which produce below 100 kilowatts that are used to directly power a home, a farm, or small business and are not connected to the grid may be classified in this class. Last, we will talk about offshore wind. Wind turbines that are erected in large bodies of water, usually on the continental shelf. Offshore wind turbines are larger than land based turbines and can generate more power. Students, you can see the figure of a turbine. These turbines you have already seen probably when you have gone for traveling in any seashore area. Uh, these turbines are mainly used to produce electricity from wind. Now let us understand how these turbines work. When the wind blows past a wind turbine, its blades capture the wind's kinetic energy and rotate, turning it into mechanical energy. This rotation turns an internal shaft connected to a gearbox, which increases the speed of rotation by a factor of 100. That spins the generator to produce electricity. You have already understood that as you have already studied the principle of dynamo. Actually, this principle of dynamo is used to produce electricity over here. Typically, standing at least 80 meters or you may say around 262 feet tall, tubular steel towers support a hub with 3 attached blade and a nacelle which houses the shaft, gearbox, generator and controls. Wind measurements are collected which direct the turbine to rotate and face the strongest wind. Yes, the strongest wind. And the angle or pitch of its blades is optimized to capture energy. A typical modern turbine will start to generate electricity when wind speeds reach to 6 to 9 miles per hour. This speed is known as cut-in speed. Remember the term cut-in speed. What is the cut-in speed? That is the speed of wind when it reaches to that particular speed when the turbine starts generating electricity. Turbines will shut down if the wind is blowing too hard, that is roughly around say 55 miles per hour or like that, something like that, to prevent equipment damage. Over a course of a year, modern turbines can generate usable amounts of electricity over 90% of the time. For example, if the wind at a turbine reaches the cut-in speed of 6 to 9 miles per hour, the turbine will start generate electricity. As wind speeds increase, so does electricity in the modern production system. Students, now you have understood that how the turbines works. Now the question is the power we are getting from the turbine, on what factors that power amount of that power depends. On what factors? There are notably three factors. First is wind speed. Already we have discussed that higher will be the wind speed within the range of cut-in and cut-off speed. Within the range, higher is the wind speed, higher will be the production of electricity generation. That also you can understand that from the idea of working of dynamo. Higher is the speed, rotation speed or wind speed, higher will be the production of electricity. Second is the cross section of wind swept by the rotor. This is also a very important point, as the higher will be the area of wind swept by the rotor, higher will be the thrust. So, higher will be the speed over here, and the overall conversion efficiency of a rotor. This is the last but not least, overall conversion efficiency of rotor, transmission system and generator or pump. Now, the question is, what is the efficiency? Efficiency means what percentage of input energy can be converted into the output energy or work done, whatever you may say. Whatever, there is a ratio of output power by input power, or say output energy by input energy. That means what fraction of input energy can be converted into the output energy. And you know, due to the working of the machineries, some power is required. Maybe there are reasons, there may be the friction, there may be the other challenges, so that some power is from the input is used up to overcome those, and rest of the thing you will get at the output. So, depending on the efficiency of the rotor, transmission system and generator pump, the efficiency of the whole turbine depends. No device, however well designed, no device can extract all the wind's energy, because the wind would have to be brought to halt, and this would prevent the passage of more air through the rotor. The most that is possible for the rotor to decelerate to whole horizontal column and of intercepted air to about 1/3 of its free velocity. Now, let us calculate the power in the wind. To proceed to that, we are over here, recapitulating the concept of kinetic energy of a particle. What is that? You know, kinetic energy of a particle is half mv square, where m is the mass of the particle and v is the velocity of the particle. Now, let us use this formula to find out what energy the air is delivering per unit time to the turbine. Let us suppose the amount of air passing per unit time through an area A with a velocity v is small m. Now, velocity of the air v means the length of the air column that is passing area A perpendicularly. Again, I am repeating, the length of the air column that is crossing that area A per unit time is V. I think you have understood. The length of the air column that is crossing the area A, per unit time is V. That means the volume of the air column is A into V. And if we suppose that the density of the air is rho, then mass of that air column becomes rho into A into V. So, here we can say small m equal to rho into A into V. Okay. That means the kinetic energy that the air is delivering per unit time is half into rho into A into V, that is the mass, into V square, half into rho A V into V square, that is half rho A V cube. So, half rho A V cube, this is the kinetic energy that the air is delivering to the turbine per unit time. So, this is the power, energy delivered per unit time, that is the power. So, the air is delivering the power half rho A V cube watts. In this graph, we have tried to show you how this power depends on wind speed as well as the rotor diameter. You can see there are three lines. In the bottommost, for the bottommost case, the diameter of the rotor is 20 meter. And second one, middle one, for the middle one, the diameter of the rotor is 40 meter, and for the topmost one, the diameter of the rotor is 60 meter. From this graph, if you take one thing constant, say let us say, suppose for the first case, say diameter is constant. If you give diameter constant, take any of the lines, you will see that the total power, total wind power is increasing with the speed. Total power is increasing with the speed for any line you see. And now if you take the wind speed as a constant, for the same wind speed, higher is the rotor diameter, that means higher is the swept area, the higher will be the power. So, from this graph, this is very much sure that what we have studied earlier, that on what factors the generation of electricity, generation of power depends. This is very much obvious that the power generation is depends on several factors. One is wind speed, another is rotor diameter or the swept area. Okay. Understood how to calculate what is the power delivered by air to the turbine, and also we have understood that whatever power is delivered by the air to the turbine, the 100% of that we cannot get as electrical power. What are the reasons behind that? That also we have discussed. Now the question is, what is the maximum amount of power then we can get out of the turbine? So that depends on the efficiency. Now what may be the maximum efficiency? Now, coming to the question of efficiency, let us understand a term that is called theoretical efficiency, you may say, or you may say power coefficient, given as C subscript P, that is called that is the ratio of power output from the wind machine to the power available in wind. So that is the output power by input power. And the theoretical calculation, that already we have shown it in the lecture note, that you will get as hard copy or say soft copy. We have shown that calculation there. We have got that, we have shown there the Cp or the power coefficient cannot exceed the value 0.593, 0.593 as a horizontal axis wind turbine. We have shown that this value, this factor 0.593 or 59.3%, this is also known as Betz coefficient. Now the question arises, can we set up turbines all over the world? Can we get this electrical power from turbines anywhere? The answer is no, because the distribution of wind energy is not same everywhere. There are several factors affecting the distribution of wind energy on the surface of the earth. The first factor we may say is, say, pressure gradient force. This is the force generated due to the difference in horizontal pressure, and it operates from high pressure area to low pressure area. Since a closely spaced gradient implies a steep pressure change, it also indicates a strong wind speed. The wind direction follows the direction of changes of pressure, that is perpendicular to the isobursts. The second factor is Coriolis force. Due to the Earth's rotation, winds do not cross the isobursts at right angles as the pressure gradient force directs, but they get deflected from their original path. This deviation is the result of Earth's rotation and is called Coriolis effect or Coriolis force. Due to this effect, winds in the northern hemisphere get deflected to the right of their path, and those in the southern hemisphere to their left, following the Farrell's law. The Coriolis force change wind direction but not its speed. This deflection force does not seem to exist until the air is set in motion and increases with the wind velocity, air mass, and increase in latitude. The third factor is centripetal acceleration. Due to inward acceleration of air towards the center of rotation on the rotating earth, it is possible for the air to maintain a curved path that is parallel to the isobursts about a local axis of high or low pressure. This is known as centripetal acceleration. The last but not the least is the frictional force. The irregularities of the Earth's surface offer resistance to the wind motion in the form of friction. This force determines the angle at which air will flow across the isobursts, as well as the speed at which it will move. It may also alter wind direction. Over the relatively smooth ocean surface, the friction is minimum. So the air moves at low angles to the isobursts and at a greater speed. Over the uneven terrain, however, due to high friction, the wind direction makes high angles with isobursts and the speed gets retarded. Thank you, students. We will meet again in the next class for the rest portion of this chapter. Till then, bye bye. Take care.